Okay. We're design team 1 and we will talk about these electronic body plate sensors. My name is Tamer.
Name's Yuval.
Evan. I'm Brett.
And I'm Ron.
Okay, so we'll start this presentation by showing you the overview of what we're going to talk about today. We will talk about some head impact statistics regarding some head concussions that caused from maybe football players. And then after that, we'll talk about technical comparison between how to measure those concussions and what technology we have today and what we're MSU presenting for the future. We'll talk about the piezoelectricity and MSU's prototype, and we will have more details about that with the circuits and the difference between circuits. So, and we start, we want to show you this video about head-to-head concussion between two players and an MSU football team, and that sometimes might lead to severe damages. Okay, so brain damages, how do they cause? From this football head-to-head concussions, head damages might cause because there is a high-level energy impulse in a very short amount of time, and that acceleration sometimes exceeds 100 g-force. And we want to make sure that players are in good health. We want to make sure that if they have concussion, if they need medical, so doctors know what's going on in a short amount of time. So for that reason, we're going to need sensors to measure those concussions to know if the players need to be substituted or need to have. Okay, that's one. So here is the technology of sensor and measuring those concussions. What we see here is a Riddle helmet sensor. If you see that arrow, these are sensors inside the helmet, and these provide us with data of the concussions to know if the players need to be helped. So the comparison here is between the sensors that we have and what MSU is providing. Complexity in terms of contemporary and MSU contemporary is very significant, so it's hard to design it and it's hard to maybe analyze it sometimes. For MSU's technology, it's very small and tiny, it's easy to design. In terms of cost, the contemporary is $1,000 per helmet, which is very huge. Comparing with MSU technology is just less than $1, which is a huge fraction between both. And then in terms of power, contemporary use battery for power, and this is a negative side because batteries in these concussions they happen in a short amount of time, and this battery gets leakages. This get more risk of having leakages because the acceleration impact increases, and that leads us to some energy, high energy. If it's very high, the energy gets shorted to ground. If you compare it with MSU, it's self-powered. It gets this power from the concussions, and whatever energy is later have it's just stored. So there is no energy leakage. So that leads us to represent the MSU solution, which is piezoelectric sensors.
So what does the word piezoelectric mean? The word piezo comes from the Greek word piezein, which means pressure. The word itself means an electromechanical configuration which crystalline materials, which pressure or physical state induces electrical charge by changing the shape and causing electrons to flow. The induced charge is proportional to a strain magnitude. When a current is applied, it causes the piezoceramic over here to change shape, causing current to flow. What happens is you apply force to a piezoelectric membrane, changing the shape. This causes electron flow to create an electrical charge. This is an electron flow, it produces current in the device.
Okay, so Brett, Ron, and I are going to talk about the major circuits within the sensor. The block diagram that you see up there shows the main elements that we're going to be talking about. On the left there is the actual piezo that generates the current that Yuval was just talking about, how that works. That feeds a current into the power circuit, which eventually logs the impact data into flash memory. So the first circuit, we talk about it, power circuit. Starting on the left side, you can see the actual current generated by the piezo flows in through here and goes through two current limiting resistors to protect the circuit. Because we want a voltage out that's positive, we implement a full wave rectification using 4 diodes. In order for the actual sensor to operate, we need a voltage above about 3 volts. Anything below this, the sensor will not react, so any noise that you experience with such a sensitive device like a piezo will be ignored. We're only after looking at high impacts, typical with a tackle in a football game. On the graph on the right, you get an idea of the type of voltages that you're dealing with. When the helmet in the study was dropped from 2 feet, you see a spike of about 35 volts. And this is well above the 3 volts, but it is also above the maximum voltage that the sensor can handle, which is somewhere in the range of 10 to 15 volts. When you have a voltage above here, the additional power is dissipated with this Zener diode DL. So because the circuit is not only providing the power, it's also providing the data. You have power that's being dissipated, you're losing data. So Brent's going to talk about how you fix that using a time dilation method.
So in order to store all the extra energy, they use a method called time dilation. So on the previous plot, the voltage output was about 35 volts. So that extra 20 volts of energy would really correspond to data that you'd be losing, which is not good. So introduce a circuit that shows time dilation, and how this works is whenever the output voltage exceeds that 10 volt limit, it creates a potential across this series of diodes, so that there will be a potential between the output and the gate of the NMOS, which will then saturate the NMOS, causing the current to flow through CS, which charges up CS. So all that extra energy, instead of being wasted, is being stored in CS. And so here's a little picture, a plot of what the data looks like. Plot A is without time dilation, so you can see that about 10 volts it starts clipping, so you're losing this data. And plots B and C show the output with time dilation, but with different values of the capacitance. So in plot B shows a capacitor of about 50 nanofarads, and plot C shows capacitance of about 0.1 microfarad. And for our application, we'd like to use a larger capacitance, so we chose, this is what we'd like to use, the 0.1 microfarad, and we like that because such a high impact with over a short period of time, it has a lot of energy, so we need a larger capacitor to be able to store that extra energy. So then going back to the, So really how it works is when the impulse is over, or the impact's over, the IP over time all comes here, and there's no more current flowing. So all the energy stored in CL and CS then dissipates through here. So we're basically just measuring the time that it takes for CL and CS to discharge, and that's directly proportional to the magnitude of the impact. So this is kind of like what the data looks like. Plot A would be showing what the impulse would look like if it was just measuring the magnitude, and as you saw, they could exceed like 35 or 40 volts, which would fry our chip. So we use this time dilation method, which clips at like the 10 volts, which was the V out, but instead of measuring the magnitude, it measures the time. So a larger impact will have a longer time versus a shorter impact, which will have a much shorter time. So they're basically just measuring the time that it takes for the capacitors to discharge, and that's how we're getting our output.
Alright, so with all the energy produced from the piezoelectric, we need to store it. And the way this works, this circuit works is it takes the energy. What you can see on the left with the op amp and the floating gate transistor, it's set up in a negative feedback configuration, and this ensures that the node VG and VS stay at a constant voltage source. On the right there, you have the right circuitry, which compares the reference voltage, which is the piezoelectric voltage, and compares that to the charge of the capacitor, CADC. And the way it works is the longer the duration of the impulse, so what we were talking about before, more ones will be written. So the comparator will consistently write ones as long as the duration of the energy is consistent. So, and as soon as the energy is gone, it'll write a 0. So what you see in the output is certain ones, amount of ones, which correlates to the level of the energy. So a couple of features of the sensor itself. This is the actual sensor. This is in the layout level. First things first, it's a complete self-power from the piezoelectric crystal or any kind of piezoelectric source. And because the piezoelectric does not provide as much current as like a battery, the overall power consumption of this is less than 1 microwatt. And therefore, since it requires no passive source, passive power source, it requires little to no maintenance. With the only maintenance is it's to physically replace the chip itself. Because if it's you're working with nanoamps and small amounts of current, the overall size of the chip is very small, and it was manufactured with a 0.5 micron CMOS fabrication process, which in turn leads to the overall size to be between 1.5 and 2 centimeters. And due to its sheer size and minimal use of components, this led to a low overall cost of less than $1, possibly even cheaper with if more chips are developed. So some typical applications that it's currently being used, obviously in football you have the kinesiology and the human physiology departments. Currently the sensor is also deployed in the medical field where elderly with weak skeletal structures can have the sensor implanted into their bones or on their bones, and you could read the data and see how the physical strength of the bone is the health of the strength of the bone. It's also being deployed in terms of the civil architecture, so not just buildings and homes, but we're talking bridges and roads. And due to the sheer expense of it, it's due to the cost. Many of these sensors can be deployed on a single structure, so you could have an overall monitor, like health monitor of the structure in its entirety. You can also be deployed in the mechanical structures, so you can monitor, in this case, a wind turbine. Caterpillar is also looking for a method to monitor their cranes and bulldozers and their overall health. And so the sensors, multiple sensors can be attached to the arm of the crane to monitor the current stress levels that it's holding. And then the last application is in the both automotive field or any industrial. And what this represents is that the sensor can literally be deployed in any type of structure that you want to monitor, be it the car, chassis, any kind of fabrication process where the product is put through constant pressure or through use. So, in any field like that. So, that's it. Does anybody have any questions?
Any questions? Yes, sir.
So with piezoelectric powered the circuitry, the only time you're going to get data is when there's a strike to, for instance, your helmet. How do you ensure that you actually get accurate information rather than someone physically taking the helmet and putting it on the ground or maybe a player slapping another player in the helmet.
Okay.
That would obviously power the circuit.
So
How do you
with the
ensure
time
that
dilation
you power the
circuit,
helmet?
you can play around with the amount of diodes you use to set your certain threshold levels. For example, going back to what Evan was saying, the minimal voltage required to power the sensor is 3 volts. Well, the more diodes you use, you set a voltage drop to each one. So essentially, you get it acts like it's like dual purpose. It acts as like a filter for both, like say something when you tap on the helmet, which is irrelevant information, versus like a full-on impact. So adjusting the voltage thresholds, you can essentially calibrate the sensor to any kind of use.
Any other questions? Okay, I have a question for when you first started out with the big picture.
Yes.
We're comparing $1,000 per helmet,
Mhm.
and that $1 from the last presentation was per sensor, it's not for the helmet.
Yeah. Oh.
So your comparison there was
Mhm.
looks like
The $1,000 was for the sensor, though,
For the sensor?
for Riddle's sensor.
not, okay.
The
By
reason.
the total helmets, like there's about 5 or 6 sensors.
5 or 6
Total
sensors,
is 1,000.
only sensors, not, okay, not for the whole
Not the
helmet.
helmet.
No, not for the helmet.
Because some most Riddell's helmets they start at like a minimum of $100 to well over like $600. So the reason why Riddell's cost is so high is because first thing it includes like a monitoring equipment, and second it has a physical wireless transmitter and using accelerometers. So at the point of impact, the transmitter will send the data straight to like a laptop to a central hub where you can process the data in real time. But the main problem with that is because it's running on a voltage source, the wireless transmitter is running on a voltage source. The main issue is that battery leakage can occur, and then the physical weight of the helmet impacts the player's performance. So the intention of our sensor is that the data will be stored onto the helmet and can actually be wirelessly sensed with like a wireless transmitter or a wireless receiver, which can just be scanned over the heads of the football players themselves.
So the wireless transmission is done in real time, at the time of impact?
That's Riddell's technology. Yeah, MSU's technology is when the player comes in, for example, to take a break, when they notice a big hit, when they sit on the bench, that the coach can just scan their heads.
Using RFID.
Yeah, using RFID. And as a matter of fact, MSCB Technologies is using the backscatter technology to have a longer range. So similar to Riddell's technology, where you can monitor the health in real time, you could also do that with a lot lower power. So that's kind of the main features of the sensor itself.
Okay, Bill, we have time for a couple more questions. Then we'll